Okay, so we're going to go back into Chapter 8, into the cumulative review exercises on page 409. And I'm going to do number 4. They have taken a simple random sample of 40 adult males, and their red blood cell counts are measured. These results have statistics, so instead of individual data observations, they've told me the sample size, the average number of red blood cells given in million cells per microliter, and a standard deviation of 0.504. The entire data set's available in the appendix. They want us to use a 0.01 significance level, meaning if our sample statistic occurs less than 1% of the time, assuming some claim, then we're going to reject that claim. So they've given us a cutoff range of probability of likelihood. So using that significance level of 0.01, and here's the claim. The sample is from a population with a mean less than 5.4 million cells per microliter. This is a standard in that area. Do the results suggest that each of the 40 males have a red blood cell count below 5.4 million cells per microliter? Okay, so claim. First thing I'm going to write, well, problem number 4. Claim, I'm going to have a null hypothesis, which is what I'm going to use to be true, and then an alternative hypothesis, which is really what I want to have happen, since I can reject the null and then in favor have my evidence support the alternative hypothesis. What do I want? It said that we want to show that the mean is less than 5.4 million cells per microliter. The mean, I'm measuring red blood cell count. I'm not taking a proportion, I'm not counting the red cells. I'm taking a measure. So the parameter is the mean for all population, the whole population. That goes on both my hypotheses. And I don't want equality, I said less than. I want that the average level is less than 5.4. And I'm going to leave off the units just for simplicity. 5.4. And then the complement is then our null hypothesis. So that would give me greater than or equal to 5.4. All right. So once I have my null and alternative hypothesis, I'm going to just quickly write down my sample statistics. So the stats, the values coming from my sample, were that they took a sample of 40 subjects. They measured and found that the average for those 40 subjects was 4.932. And that was in measure of million cells per microliter, with a standard deviation, so they vary on average. Adjust my pencil. There it is. Bear with me. So the average they vary is 0.504. So 4.937. All right, so those are the statistics I was given. That's my evidence, and I want to measure the strength of my evidence. This is the evidence, hopefully against the null hypothesis, so I can reject the null hypothesis in support of the alternative, what I want. If this is evidence and I want strength of my evidence is measured in probability. How likely was I to get these values, these test statistics, if we assume the null hypothesis is true? So the strength is measured in probability. That's called our p-value. Just to write it out in terms of probability that our test statistics, so let's use x bar, a good estimator, point estimator for the average for the entire population. How likely was it that our average is 4.9 937, that's a 4.937, given the true mean is actually 5.4. Now, what else would be evidence? If I have 4.937 or smaller, that would be in support of my alternative. So 4.937, and I always put smaller. Why? Because the probability that the average for my sample is actually exactly 4.937 would be 0. I need an area underneath the curve to have probability. So I'm taking a region in support of my alternative hypothesis. I just need a density curve. To get the density curve, let's check that we planned out a simple random sample. And number 4, those are the first 4 words. A simple random sample was taken. So yes, somebody who planned this out knew that we needed the sample to have randomness. And then 2, unlike with proportion, we're not going for binomial. I'm going to go for, do I know anything about the actual population's distribution? Is the population distribution, do I know that that is normal? And sometimes we do know something about the shape of the distribution for all possible values, all possible subjects, but it's rare. Now I have the central limit theorem that says if at least size 30 sample, then the student T distribution approximates the distribution, and I have a sample of size 40, so we're good with that. Just in case I take a smaller sample, I need to check outliers and rough symmetry. And in either case, at least 30 or less than 30 with no wonky values would be able to use the student T distribution. So that's giving us, since we have at least 30, that if I put all possible sample means from samples of size 40, took their histogram, that it would be approximately a student T. Now student T's vary. The larger the sample, the more normal this becomes. So I always write down what the name of this is. Student T to help me out. Now it changes as the sample size changes, and that's called our degrees of freedom. It's dependency of the variables upon each other. It's 1 less than the sample size. So sample size minus 1. In this case, sample size is 40, so I have degrees of freedom, 39. That's the shape. I always do shape. I always put center. The X bar, our sample mean, is an unbiased estimator of the true population mean. So in other words, the center of the distribution of all possible sample means is 1, the mean of the population, which we're assuming from our null hypothesis is 5.4. And that takes care of shape, center, spread, the standard deviation of my sampling distribution. Let's just label. I like labels. Distribution for all X bar. This is actually sigma, the standard deviation of the population divided by the square root of n. Gets a little tighter. Now I don't know sigma, but I do know S sub x. All right, so just to recap, to have a little bit more space, all X bars are going on here. That's called a sampling distribution. All possible sample statistics X bar. When n is equal to 40 for X bar, they go on a number line. We pass the conditions because we had at least 30. There's the shape, student T, with degrees of freedom equal to 39. Center is going to be the 5.4. The spread of all those is sigma over square root of n. We don't know sigma, so we use my sample, it's the best I've got, over n. The sample standard deviation was 0.504. 0.504 divided by the square root of 40. Just quickly to calculate that. 0.504 divided by the square root of 40. Boom. Oh wow, 0.08 again, like the previous problem. Okay, so about 0.08. And that's in nice units. I'm not putting units down here. Oh, I know one more. I know one of these x bars. I know mine. X bar was 4.937. Here's 5.4. Where are you? 5.4 on the number line. We're going up and down the axis by 0.08 to get those percentages. Wow, so I need to get all the way to 4.937. That's going to be way down here. 4.937 is my sample statistic, my contribution to the sampling distribution. And the p-value is the likelihood, not that we're equal to, but that we're equal to 0.4937 or more extreme in the direction of what we want. So this is our p-value. This is the area underneath my density curve. This is the probability. It's the strength of my evidence. It's the area underneath a student t distribution. This is the fun part because the TI doesn't allow you to enter in the center and the spread for this particular student t. It does only the standard t distribution. So you've got to do a little bit of conversion here. I'm going to convert to a standard normal. So 0 goes in the middle. 1 is the standard deviation, and this is the standard t distribution. Still degrees of freedom is 39, but I need to figure out what's 4.937 on the standard one. That means I need its t-score. So 4.937 minus, for t-score here, minus the mean. Mean was 5.4. So how far away are you? And then divide by the standard deviation, which we got is 0.08. So the t-score is, it's 4.937. 937 minus 5.4. That's the numerator. I didn't put parentheses, so I'll just go ahead and calculate that. Divided by 0.08. The t-score is negative 5.79. Negative 5.79. So this value on the standard norm, the sampling distribution of all x bars, with this is the center and standard deviation, has to become the standard t distribution. This value translates to its t-score of negative 5.79. Same p-value. This is still the p-value. We haven't changed anything about the shape. We just kind of shifted over and did the conversion. So the strength of my evidence is going to be the p-value. That's the area under the curve. So I'm going to use second distributions. I'm going to look for t, because I'm using a student t distribution, not the height of the curve, but a cumulative density function. That's what I need. It says, where would you like me to start shading? I'd like you to start shading at negative infinity. That's my idea of negative infinity. Good. Where would you like me to stop shading? At negative 5. Did we say 97? 79. 79. And then it says, what degrees of freedom would you like me to use? And I'm going to tell it 39. Doesn't ask me for my mean and standard deviation. That's why I had to do a t-score, because it's assuming the center is 0, standard deviation is 1. Paste that to the main screen, calculate, and I get a probability using scientific notation. I have 6 zeros and then a 507. this area, this p-value, that area underneath curve, using TCDF. Get more lead. I used TCDF. I used negative e to the 99. I used negative 5.79 as the upper, and the degrees of freedom of 39. It gave me 0.000005. The likelihood that I would get a sample having an average, and that's an X bar, of 4.937 as the count of my red blood cells, if the true average for the entire population is in fact 5.4, is really small. It happens way less than my significance level of 1% of the time. So I'm going to reject the claim. Reject the null hypothesis, and support the alternative. So I can say that the evidence supports the claim, this is what we wanted, that the true population's average red blood cell count is less than 5.4, and I believe that was in million cells per microliter.